The world thought it had silenced Mount St. Helens. But 44 years after the explosion that erased forests and rewrote maps, the mountain is stirring again. The United States Geological Survey has issued a red alert, the highest possible warning, signaling that one of Earth's most dangerous volcanoes may be ready to wake. Beneath its snow-covered crown, magma is rising, gas is building, and the ground itself is swelling. The clock is ticking, and scientists can feel the mountain's pulse quicken. Could the most notorious eruption in American history be about to repeat itself? The mountain wakes. At first, it was just a whisper, small tremors deep below the Cascades, too faint for anyone but machines to hear. But by late spring, seismographs began to dance. Clusters of earthquakes rippled beneath Mount St. Helens, each one a heartbeat in the mountain's restless body. The frequency doubled, then tripled. To seasoned volcanologists at the USGS Cascades Volcano Observatory, the pattern was unmistakable: magma was moving. Gas sensors stationed in the crater registered sudden spikes in sulfur dioxide and carbon dioxide, chemical signatures that betray molten rock rising toward the surface. High-resolution satellite imagery revealed subtle swelling of the summit, barely a few centimeters at first, but spreading outward like a slow breath. Thermal cameras caught pockets of heat around fumaroles, where steam hissed through vents that had long lain dormant. The mountain that had slept since 2008 was breathing again. Inside the observatory in Vancouver, Washington, analysts pored over data streams in silence. They had seen these patterns before, though never identical. Each volcano speaks its own language. St. Helens communicates through quakes that start deep and climb upward, through gases that pulse in rhythm with subterranean pressure, through minute deformations of rock that computers can measure but the eye cannot see. When these signals converge, there is only one responsible course of action: raise the alert. And so, after weeks of escalating activity, the USGS raised Mount St. Helens to red alert, a classification reserved for an eruption that is imminent or already in progress. For residents of Washington state, it was déjà vu written in ashen memory. The official statement was calm, factual, restrained. Yet between its lines lay urgency. Scientists warned that magma had repressurized chambers beneath the crater. Volcanic gas ratios hinted at fresh magma rather than residual heat. Even ground deformation suggested inflation across several kilometers. The signs pointed not to minor unrest but to a system loading energy for a potential explosion. For many Americans, Mount St. Helens is a symbol frozen in time, an open-jawed crater framed in snow, a national monument to destruction. But geology does not respect nostalgia. Deep below, basaltic magma rises from the subducting Juan de Fuca plate, melting crust as it ascends. This is no dormant relic, it is a living engine. Local news helicopters hovered above the mountain, catching plumes of vapor curling from the summit. Some mistook the scene for eruption smoke, but the USGS clarified, not yet. What viewers saw was steam venting from fractures widened by pressure. The volcano was flexing its muscles. Scientists compared current readings to archived data from early 1980. The parallels were unsettling: similar depth distributions of earthquakes, similar rates of ground uplift, even comparable gas compositions. The difference was the sophistication of today's monitoring network. Back then, predictions relied on analog instruments and field notes. Today, satellites, drones, and GPS arrays capture every twitch in the Earth's crust. Still, even with advanced tools, prediction remains uncertain. A volcano is an orchestra of variables: pressure, viscosity, gas content, and conduit geometry playing in shifting tempo. One wrong interpretation, and humanity learns humility again. Is the mountain warning us, or merely reminding us that it never truly sleeps? Echoes of 1980. To understand the dread behind the current red alert, one must revisit the day the sky fell. On May 18, 1980, Mount St. Helens exploded with the force of 500 atomic bombs. In a single instant, the volcano's northern flank collapsed in the largest landslide ever recorded. The sudden release of pressure uncorked superheated gases that tore through forests at 600 km per hour, flattening trees across 230 square miles. Ash darkened skies from Washington to Oklahoma. Rivers clogged with mud and timber. 57 people died, many of them scientists and photographers who had come too close in pursuit of knowledge. The event transformed not just the mountain but the science of volcanology itself. That eruption began, as this episode does, with subtle seismic murmurs. 4 months, quakes rattled the region while a bulge swelled on the volcano's north flank, an ominous blister growing outward by 5 feet a day. When it finally gave way, the side of the mountain slid, depressurizing the magma chamber and releasing a blast that traveled faster than sound. Entire ridgelines vaporized. The top 1,300 feet of the peak vanished, leaving a horseshoe-shaped crater still visible today. 4 years afterward, the landscape looked lunar. Yet from the ashes came rebirth. Scientists established the Mount St. Helens National Volcanic Monument to study ecological recovery. Lupins pushed through ash fields. Elk returned to graze among dead trunks. Nature rebuilt itself molecule by molecule. But the mountain never stopped rumbling. In 2004, a new dome began to grow within the crater, extruding lava like a giant tooth. It puffed steam and ash intermittently until 2008, then quieted apparently content. Now, as instruments detect swelling once more, scientists recognize a familiar cycle: dormancy, inflation, eruption, renewal. For residents who lived through the original disaster, the red alert brings old memories rushing back: the thunder that shattered dawn, the darkness that turned noon to night, the grit of ash grinding between teeth. Many who were children then now tell their own grandchildren the story. They remember how fragile civilization looked beneath a sky filled with fire. Technological progress offers reassurance but not immunity. Modern monitoring can issue warnings hours or days in advance, yet once pressure exceeds the threshold, no force can stop it. The magma will find release. Whether it emerges in a slow dome-building phase or a catastrophic explosion depends on the delicate balance of gas and viscosity inside the mountain. Volcanologists analyze that chemistry like doctors reading a patient's vitals. Current gas ratios suggest magma rich in silica, which traps gases more effectively, an indicator of explosive potential. Meanwhile, deformation maps show inflation concentrated under the crater rather than the flanks, implying upward pressure rather than lateral collapse. If accurate, the next eruption might resemble a vertical column of ash rather than a sideways blast. But nature has a habit of rewriting expectations. The parallels between 1980 and now haunt every briefing. The same subduction forces still grind offshore. The same magma reservoirs refill. The same forests stand in the path. Each tremor beneath St. Helens carries the echo of that morning when the mountain tore itself apart. If history can repeat in geology, how many warnings do we truly get before the earth demands remembrance? Science in the shadow. Inside a gray concrete building in Vancouver, Washington, a team of geologists works around the clock, their eyes fixed on a wall of screens alive with trembling lines and shifting colors. These are the instruments that let humanity hear the mountain breathe. Each red flicker marks a tremor, each curve in the data, a heartbeat in molten rock. The USGS Cascades Volcano Observatory has become the mountain's interpreter, translating seismic whispers into warnings that could save thousands of lives. The data arrive from a network of sensors scattered across the Cascade Range, GPS units anchored to rock outcrops, gas detectors perched near vents, and infrared satellites orbiting hundreds of kilometers above. Together, they form an electronic web capable of detecting movement less than the width of a coin. When the mountain exhales, this system knows. Yet for all this sophistication, prediction remains an art balanced on science. Volcanologists must read not just numbers but patterns, intuition built over years of watching magma rise and fall. They compare the present to hundreds of past events stored in global databases. Does this cluster of quakes mimic a dome-building phase? Does this gas ratio suggest new magma or reheated residue? Every data point is a clue in a mystery with no guaranteed ending. Drones now play a crucial role. They hover over the crater, collecting thermal imagery too dangerous for humans to obtain. These machines can fly through fumes and return with microsamples of gas that reveal the chemistry of the magma below. In one recent mission, a drone captured footage of faint orange glow deep inside a vent, a sign that heat is migrating upward. Satellites contribute their silent testimony. Using radar interferometry, they measure surface deformation with millimeter accuracy. When compared over weeks, these images show the mountain's skin stretching and relaxing like a living muscle. The current sequence shows steady inflation centered beneath the southern rim, consistent with magma pressurization. This technological vigilance is born from the humility learned in 1980. Then, instruments were primitive, and communication lagged hours behind the data. Today, algorithms flag anomalies in real time, and emergency managers receive instant alerts. Still, nature resists full comprehension. A volcano may tease for months, then subside without erupting, or it may detonate with little warning. Science narrows possibilities, it cannot eliminate them. What has improved most dramatically is coordination. The USGS, NASA, NOAA, and local agencies now share data streams through a single cloud platform. Thermal anomalies, seismic trends, and gas readings merge into three-dimensional models that visualize magma pathways like arteries pulsing inside the crust. This allows planners to simulate eruption scenarios and update hazard maps every hour. Beneath the technical calm of the command center lies a human tension. Every scientist knows that a misjudgment could cost lives or credibility. To raise a red alert too early invites panic and economic loss. To raise it too late invites tragedy. The decision is collective, the responsibility immense. Volcanology, for all its equipment, is ultimately a discipline of listening. It teaches patience, respect, and restraint. Mount St. Helens speaks in pulses of gas and quakes. Scientists answer with vigilance and humility. They know the mountain owes them nothing. When data speak in riddles and the earth itself holds the code, how much certainty can humanity truly claim before the next roar?